Physics 211 Motion of a falling object. The purpose of this lab is to analyze the motion of an object that falls from rest using the Tracker app and comparing the observed motion with two computational models, one with gravitational force only and the other with both gravitational force and drag force. The fundamental principles used throughout this experiment are Newton's second law, which states that force is equals to mass times acceleration. In terms of momentum, it is the net external force equal to the change in momentum of a system divided by the time over which it changes. A preview of the main results obtained in this experiment shows that the computational model that considered both gravitational force and drag was similar to the results of the observed one compared to the computational model that didn't consider drag. And fundamental principles. Under Newton's second law, we use the net force, which is equals to the gravitational force plus the drag force. The net force is also equals to the change in momentum over the change in time. Net force is also equals to mass times change in velocity over change in time, and F net is also equals to mass times acceleration. Gravitational force. The force due to gravity is equals to mass times gravity times j hat, where j is 9.81 meters per second. Drag force. The force due to drag is equals to minus b times the modulus of v, which is to the power 2 times v hat. The other useful formulas is the final velocity, which is equals to initial velocity plus acceleration times change in time, and then there's the final distance, which is equals to the initial distance plus average velocity times change in time. Physical errors and assumptions. Human error. The parallax error. If an observer is not positioned directly in line with the object's path or the measurement markers like rulers or grids, parallax error can occur. This happens when the position is viewed from an angle rather than a direct line of sight. There's the judgment of free fall start endpoint, which is a human error that can occur when determining the exact starting point or stopping point of the object. Then there's computational error that may occur, such as precision errors in measurement. When using real-world data and computations, the measurements themselves may contain errors due to limitations in the measuring instruments. Then we have assumptions that we made, which include that the object falls in a straight line, i.e. directly downwards, only falls down in the y-axis, and the x and z axis remain a constant of 0, 0. The second assumption is that it's a point-like surface, meaning that the ball surface is considered smooth and round to make calculations easier. The system is the tissue paper, the surroundings is the earth and the air. The initial conditions are 0, 0, 0 for position, velocity 0, 0, 0 meters per second, and time 0 seconds. The final conditions are also mentioned. I used Tracker in order to determine the exact position as it falls down to the ground. I then changed the coding in GlowScript, such as the fnet to equal to w, in order to obtain a position time graph of when gravitational force is acting on the tissue only. Then using GlowScript, I was able to add other key information such as the ball velocity, the formula for drag force, in order to determine the computational data when drag is present alongside with gravitational force as the object is falling down. I then plotted all the graphs together in order to compare them, from which I was able to realize when gravity was only involved, the tissue paper fell down the quickest compared to in real life, and the computational model, which included gravity and drag, which proves that drag acts in the opposite direction of the gravitational force and slows down the velocity of the object falling. What if? If the object was thrown downhill or started from rest, the end velocity would remain the same. Only drag and weight are important. Initial velocity is irrelevant. Tossing an object downward would cause it to slow down until it achieved terminal velocity as the model with 0 beginning velocity, according to our computational model that included drag. To answer the what does it mean question, when the force of gravity acting downwards is equivalent to the force of drag pointing up, terminal velocity occurs. This indicates that an object traveling at its terminal velocity experiences no net force. Drag air resistance is a crucial component of terminal velocity, hence the model that takes it into account depicts terminal velocity. Conclusion. We used Newton's second law, the gravitational force, and the drag force to model the motion of the tissue paper as it falls down. We recorded and analyzed the vertical motion of a tissue paper using Tracker and compared this data to computational models from GlowScript. We also noticed that in the real world, drag is present along with gravity that acts towards the center of the Earth. Thank you so much.